As we go on in Chapter 3 to Topic 4, Exponential and Logarithmic Equations, we're going to use many of the skills we just had to solve these equations. Let's look at the objectives. Use like bases to solve exponential equations. Use logarithms to solve exponential equations. Use the definition of a logarithm to solve logarithmic equations. Use the one-to-one property of logarithms to solve logarithmic equations, and then solve applied problems involving exponential and logarithmic equations. So again, reading these because there's so many uses now of what we've just went over. All right, solving exponential equations by expressing each side as a power of the same rule. And we said that if our bases equal each other, then our exponents equal each other. All right, so let's look at an example. So there is example 1, and we're going to the whiteboard to work it out. So I'd like you to copy this down. So here we have a base of 5 and a base of 125. Well, we want to see if we can get the bases looking alike. So this one is okay. 5 to the 3x minus 6. And would you go along with this? 5 to the third power. So we've got our bases now to look alike. The exponents should equal each other. 3x minus 6 equals 3. Transpose that, becomes a 9 on this side, 3x. So x will equal 3. Just a little algebra there. Now here our bases don't look alike, but we can make this 8, 2 to the third power, and this is x plus 2 equals 2 to the second power, and this is x minus 3. So we know we can bring this, we're going to multiply, so this becomes 2 to the 3x plus 2 equals 2, bring this out, 2 to the x minus 3. So our bases are the same, so our exponents must equal each other. So this would be 3x plus 6 equals 2x minus 6. And we're going to subtract 2 x's from both sides. We get x equals 12. So again, knowing this first technique will be very useful. Let's go back and check our answers. And there they are. For another rule we worked with was to using logarithms now to solve exponential equations. Well, we want to isolate the exponential expression. May have to use a little algebra for that. And then we're going to take the logarithm of both sides. In some cases, we're going to use common logs, base 10, or we can use natural logs, base e. And then we solve for the variable. All right, let's take a look at one of the examples here. Example number 2. Let's write it up big. It's 5 to the x power equals 134. So what do? Well, we're going to convert this to, let's use natural logs. That's what they use. Natural log of this side natural log of that side. Now we know one of the rules is we take the exponent, put it out in front. So we now have x natural log of 5 equals the natural log of 134. So we're just going to divide both sides by the natural log of 5, natural log of 5, and then x will get our answer, which will be actually approximation. And to save time, just look at what they've done here, and they get x is approximately 3.04. Now you want to be sure you try your instrument out that you're getting this answer. I just did, and it checks out. All right, let's go on. Now for example 3, we're going to use base 10, our common log. Go to the whiteboard. Now the log of 10 to the x power equals log of 8,000. Now notice this arrangement, because our base here is 10, log base 10 of 10, taking our exponent, moving it out in front, this just becomes a 1. So this side's just going to become an x equals the log of 8,000. And let's look at what they show here too. You've seen it, hopefully you have some notes on it. So again, there's a 10 there. We take the x, put it out in front. This arrangement, as we've said, is just a 1. So our log of 8,000 is 3.90. They want it approximated to 2 decimal places. Now, for example 4, they write it out very well here. So let's just take it in steps and follow it through. So there is our equation in exponential form. A base to an exponent equals a base to the exponent. Now, the bases are not the same. So what do? Well, we convert it to its log form, and we're going to use the natural log. Now, what do we do with the exponent? We take the exponent and put it out in front, and that's what you see in this step. And this exponent goes out in front, and that's what you see in this exponent. Now, what we want to do is take the parenthesis and in a sense get rid of the parenthesis by multiplying 2x by the natural log of 3. And that's what they've done here. And then a negative 1 by the natural log of 3. And then the same thing to the other side. Now, what do you notice? You want to get all the x terms over to one side and all the non-x terms over to the other side, and you do so by just transposing. So now we have a term here with an x value, a term here with an x value. We're going to factor that x out of this, and we end up with this. So now, how do we find what x is? Well, we're going to divide both sides by this, which is what they're showing here. So what does x equal? Well, the exact answer is this. Put that carefully into your calculator and see if you get this. That would be a value of x. But again, the exact answer is this. So pause, look it over, and see if in fact you can follow, which is a somewhat rather complicated exponential equation that we're solving by using logs. Using another skill from our past lessons, definition of logs to solve logarithmic equations. We want to express the equation in its log form and use the definition of logarithms to rewrite the equation in exponential. So we're converting it from log form to its exponential form, solving for the variable. And remember, we can't have a value that is 0 or negative. All right, let's look at an example here. Example 5. All right, this is example 5, and we see the problem, and we'll go to the whiteboard. So there it is in standard log form. We're now going to put it in exponential form. Our base is 2. Our exponent is 3. And our answer is x minus 4. So simple conversion. Well, 2 to the third is 8. X minus 4. We're going to add 4 to both sides, and we get x equals 12. Let's check it out. X equals 12. Now, let's do the check because they do it here as well. So 12 minus 4 is 8. Is the log base 2 of 8, is it 3? And the answer is yes. If you put this in exponential form, you would get 2 to the third power equals 8. So our solution set for x is 3. Again, I think this one's a tad easier than the one we just did. All right, example 6. Let's go to our whiteboard. We're using natural logs here. So the first thing we want to do is isolate the log part on the left. So we're going to divide this side by 4 and this side by 4. So now we have the natural log of 3x equals 2. Well, what is the base of our natural log? Well, that is e. So converting this to its exponential form, it will be e to the second power equals 3x. So how do we solve for x? Well, we divide both sides by 3. So we get x equals e to the second divided by 3. Now again, this is the exact answer. We're going to get an approximation. And if we go back here, there's our exact answer. The check is a little hard to follow, so we'll use the whiteboard to review it with you. So here, the 3's are going to cancel out here. So we'll just erase them. So we now have this. 4 natural log of e to the second equals 8. Now remember that the base of the natural log is e, and this configuration is just the 1. And in a sense, we could take that 2 and put it out there. So this then becomes 4 times 2 equals 8, and 8 equals 8, and therefore that checks. So this is what they're showing there, and it's a little hard to see because this should indicate a little dot there, and I guess this dot doesn't come out well. So what does x equal? X equals this. And if you put that in the calculator, it's 2 point something, which is an approximation, but it looks like they're looking for the exact answer here. Now in example 7, this gets a little complicated too, but I'll write it out for you and put it on the whiteboard here. So the first thing we want to do is put this in its condensed form. So this is going to be log of x times, because it's plus, x minus 3 here, and that equals 1. Now we're going to convert it from its logarithmic form, and this is base 10, to its exponential form. So 10 to the first power, there's your exponent, there's your base, equals the answer. Now I'm going to distribute that, x squared minus 3x. This is the answer, this is the base, this is the exponent. So now I'm going to move everything over to this side, x squared minus 3x. Transposing this becomes a negative 10. And on this side it's going to equal 0, but I like the 0 on this side, and we'll just clean it up a little bit now. You can see where it came from. Okay, so what do? Well, this is factorable. So x, 5, 2. We need a minus here and a plus there. Equate each of the factors to 0. Here x equals a negative 2. Here x equals 5. Now keep in mind that if x were a negative 2, that would make this log part not a real number. So we exclude x equals negative 2, and our answer is x equals 5. Now let's go back to the whiteboard and clear this up, and we see that this is the valid answer, while this one isn't. And let's see what they're going to show us here. In the next slide, they're showing us the proof that negative 2 is not a possible answer. So the only answer is a positive 5. All right, using another property here, the 1-to-1 property of logarithms. That is, if you have a log on one side that's equal to a log on the other side, you can just divide out the logs. And we'll show you this in the next slide. Now here, again, example 8, and this is rather complicated, so we'll work it out using the work that's there. And we'll want to copy it down step by step, and I'll explain it in some detail. So here is what we want to solve. So there's a log equals a log, and this is the expanded form. So the first thing, we want to write the right side in its condensed form, and since it's negative, this part is division. We're going to make this the denominator. So now it is the natural log of something equals the natural log of something. So in a sense, we can divide out the natural log. And then it just becomes this. Now, again, we're going to use some algebra. In a sense, this is like over 1, and this is a fraction. And we said we can cross multiply here. So they're doing it by multiplying each side by this common denominator. But if we can cross multiply here as well, so this side, 1 times this, just becomes this. And 3 minus x times x minus 1 becomes this. Or if you just multiply both sides by this, on this side they cancel out, and you're left with this. Now, what do? Well, now you FOIL this, and let's practice FOIL. Our first is x squared. Our outers is a positive 1, an inners a negative 3x, so this becomes a negative 2x, and then our last becomes a negative 3. So we bring this up to this side, and now what we want to do is put it in standard form. We're going to take our positive 7x over to this side where it becomes a negative 7x, and a negative 2x gives us a negative 9x. Transpose this to the other side, where a negative 23 becomes a positive 23, and a 3x, negative 3x, gives us a 20. Okay. We factor this, equate each of the factors to 0, and we get that x is 5, or x could be 4. Now, do these values, a positive 5 and a positive 4, fit into our logarithmic expression? That is, this cannot be a 0 or a negative number when you finish. And here a 4 would work, here a 4 would work, and so it would work there. And if the 4 works, the 5 works. Now, what they do in the next few slides, and we're going to save a little bit of time, is to say that 5 is a true solution because of what we've just said, and 4 is also a solution of what we've just said. So our solution set for this is going to be the 4 and the 5. Okay, we're saving hopefully a little time here. And for our last example, we have an application problem. And we'll use, again, what they have here, because they do a nice job. I'll explain it item by item. So this is the compound interest formula, and A is the future amount, P is your initial starting principal, 1 is in the formula, our rate is 8% that we're going to convert to a decimal fraction, our N is the number of times during the year that it will be compounded, and we're saying it's quarterly, so our N is 4. and now we substitute. So it's going to grow to our future amount of 3,600. We're going to start off with $1,000. We know it's going to be compounded quarterly. So our n up here, where it's 4 there, it's also 4. So we get 4t. So we can do this in our calculator, and this ends up being this. All right, so what happens now? Well, to simplify, we can divide both sides by 1,000. And this just cancels out here in a sense. And we get this. Now, we want to put this in natural log form, which is what they're doing here. And then what do we do with our exponent here? We take it, move it in front, and then what will our answer be? Well, we're going to divide this side by the 4 and the natural log of 1.02, which they're showing here. And then we've isolated our t, both sides again. And it's approximately this. Now, what does that mean? Well, that after 16.2 years, the principal of 1,000 will grow to an accumulated value, your future value of 3,600. Okay, one more to go. That'll wrap us up here. Example 10. The percent of an adult's height attained by a girl who is X years old can be modeled by this logarithmic function, where X represents the girl's age from 5 to 15, and the function represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? So here we're going to do some substitution. The F value here is 97, which is a percent. We don't convert it to its decimal form. And we get this. So, again, we're going to move the 62 over to this side as a negative 62, and 97 becomes 35. Now, to get rid of this 35, we're going to divide both sides by 35. And I don't have room to show it here, but I guess I do. These just cancel out and become a 1. So now I have 1 equals log of x minus 4. And I like the whiteboard. We're now going to convert this, after I kind of clean this up here, to its exponential form. Now notice this is log of base 10. So our base is 10. Our exponent is 1. And our answer is x minus 4. Well, 10 to the first power is just 10. Wanted to erase that. So we get x equals 14. So not too bad when, using the rules that we've had and the properties and solving applications using exponential and logarithmic forms. And we'll wind this up.